Alright folks, today we're going to talk about predicting double replacement reactions. Yesterday, or last podcast, you did single replacement. Today you're doing double. Right? If you remember our discussion of this picture, we could have people where the two young ladies said, well, we want to swap dates. Right? That's what a double replacement reaction is that two compounds. So we could look at this couple as being a compound and the couple on the right being a compound. And what happens is the two cations, let's assume those are the two boys, the two cations swap. Right? So they're now leaving the dance with different anions. So, does it happen? One of the questions is, does this actually happen? Are they going to swap or aren't they going to swap? Well, that's one of the things we have to figure out. So how do we figure that out? Well, we have to go through a multi-step process to make this happen. The first thing is we have to predict the products. So let's look at this particular reaction. Now, it's really easy to do this when you have names, because here you have sodium chloride and silver nitrate, and all you have to do is swap the words. So it's going to produce silver chloride and sodium nitrate. That is extremely easy. All you have to do is swap the first two words, because the first two words are going to be your cations. Right, so the first thing we have to do is predict the products. The second thing we have to do is say, does the reaction actually happen? Well, for the reaction to happen, both of the things on the left have to be aqueous. Remember, aqueous means that that is dissolved in water. And one or more of the products has to be a solid, or water. They can't both be aqueous. If they're both aqueous on the right-hand side, nothing happens. So we check this first because we don't want to go through the rest of this process if it's not going to happen. Okay? So the rest of the process says we have to take the names and change them to symbols, we have to balance charges, and finally we have to balance the equation or balance the atoms that are on both sides. So how do we decide if this happens? Well, we have sodium chloride and silver nitrate. So what we have to do is we have to pull out our solubility table, folks, and our solubility table is on one of the first few pages that you had in your packet. So pause the video, pull out your solubility table, then we'll keep going. Alright, we have sodium chloride and silver nitrate. So what we have to do is come down here to sodium and look for sodium chloride. Chloride is right here. So sodium chloride says that we have something that is aqueous. And our other one is silver nitrate. So let's go up and look at silver, which is right above sodium. And we have to look all the way across to nitrate, and it says that nitrate is aqueous. So when we look at our equation, we now know that both sodium chloride and silver nitrate are both aqueous. But what about our products? What about silver chloride and sodium nitrate? Well, one of them better be a solid. So let's look at silver chloride. Oh, silver chloride is going to be a solid. Great. And what about sodium nitrate? Well, sodium nitrate is still aqueous, so we don't have to worry about that. But the key here is that, that silver chloride is going to be a solid. Right? So let's actually go back and do this. We've already predicted the products, and we have said it happens, and the reason we know it happens is the two things on the left, the reactants, are both aqueous, and one of the products is solid. So let's go and let's see, I have room down the bottom. Let's go ahead and do this. I'll do my names to symbols, which is sodium chloride, which is aqueous, plus silver nitrate, which is AgNO3, and that's aqueous. Right? Everything, the sodium and the silver both have +1, the chlorine and the nitrate both have -1, so everything's cancels. So we're going to swap partners. So we have the silver, which is going to bond with the chlorine, and we're going to have the sodium, which bonds with the nitrate. So we've said it happens, and the reason we know it happens is because the silver chloride becomes a solid, and the sodium nitrate remains aqueous. So the driving force behind this is the silver chloride. Now we have to balance our charges. We've already done that. They're all ones. And we have to balance the atoms, which we have one of everything on both sides. So we're balanced. So that's it. How about iron chloride and ammonium nitrate? Well, again, we have to pull out our solubility table to figure this out. But the first thing we do is we look at the words, which are iron, and we look at ammonium, and we're going to cross them. All right? So they're going to go with the different partners. So our iron 3 is going to go with the nitrate, and the ammonium is going to go with the chloride. So we have iron 3 chloride and ammonium nitrate. Iron 3, and we come across to chloride, is aqueous, and ammonium nitrate. Ammonium, and let's come across to nitrate. By the way, folks, I'm one of those people who I do this pretty quickly. Notice all of your nitrates, they're all aqueous, and all of your sodiums are also aqueous, and all of your potassiums are also aqueous. So that just kind of helps when you're looking at things. Anyway, so our iron 3 chloride and our ammonium nitrate are both aqueous. So that's good. So what are we producing? Well, we're producing ammonium chloride and iron nitrate. Ammonium chloride is up here and it's aqueous, and iron 3 nitrate is, hello, where's my pen? There you are, thank you, is aqueous. Oh, everything is aqueous. So when we do this, we realize that since they're all aqueous, nothing happens. So here we can just say no reaction. Right. So we didn't have to go and write down all of our symbols. We didn't have to balance everything, etc., etc., etc. We were just able to say the reaction didn't happen because we looked at our solubility table. All right. Let's try another one. Let's try potassium phosphate and barium chloride. See if you can do this one. Pause the video, folks. See if you can do it. All right. Potassium phosphate, barium chloride. Potassium phosphate, we know, is going to be aqueous because anything with potassium in it is aqueous. So potassium phosphate. Where am I? Guys, I really hate it that you can see this and I can't. Thank you. Potassium phosphate, and I can't remember what the other one was now. Barium chloride. All right. So we come up to barium, and we look for chloride, chlorate, chloride, chloride, and they are both aqueous. So now we come over here and let's look at what our products are going to be. And they're going to switch partners. So the barium is no longer going to be with the chloride. Let's look at this. The potassium and the barium are switching places. So we're going to have potassium chloride and barium phosphate. Potassium chloride and barium phosphate. Potassium chloride is aqueous, and barium phosphate is a solid. Barium phosphate is the solid. Okay. So barium phosphate is the solid. So those two together are going to be the solid. So now we actually have to go through our process. So we have potassium, which is K, phosphate, which is PO4, and we're putting it together with barium and chlorine, barium chloride, which produces potassium chloride. Our partners are switching, remember, plus barium phosphate. Now, I happen to know that barium phosphate is going to be my solid. Everything else is going to be aqueous. All right. And now the next thing I have to do is balance my charges. Well, potassium has a +1 and phosphate has a -3. So we crisscross them, so it's K3PO4. And barium has a +2 and chlorine has a -1, so we crisscross them and we get BaCl2. Now potassium chloride's 1 and 1, one positive, one negative. And barium is +2 and -3, so it's Ba3, PO4, 2. So I've now balanced all my charges. So now I have to go back and say, well, let's make sure that I balance all of my equations. Well, let's see. I notice that I have 3 bariums. That gives me 6 chlorines. That gives me 2 of these. And I have to have 2 PO4s to satisfy the other side. So I'm now balanced. And I have included, whoops, I forgot something. Barium phosphate's a solid. So I have to put a solid after that. All right, everything is balanced. We should be good to go. Okay, let's look at the next one. The next one says we're dealing with silver nitrate and sodium carbonate. Silver nitrate, sodium carbonate. Sorry, I went the wrong way. Silver nitrate, sodium carbonate. Silver, 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 silver nitrate. Silver nitrate. Silver nitrate is here. Silver nitrate and sodium carbonate. And sodium carbonate. Carbonate is going to be really close. It's only 3 up. Okay, cool. So that's good. And what's going to happen when we put those two things together? Well, we're going to get... Sorry, I went the wrong way, folks. My fault. Silver nitrate, sodium carbonate. So the silver and the sodium replace each other, so it's now sodium nitrate and silver carbonate. Sodium nitrate, and silver carbonate. Silver carbonate. Ah, silver carbonate is a solid. Fabulous. Everything else is aqueous, so this is actually going to happen. So let's go ahead and do this. So silver carbonate, these guys, silver carbonate is going to be my solid. So let's go ahead and write these down. This is silver nitrate, and that's aqueous, plus sodium carbonate, NaCO3, and that's also aqueous. And that produces, we swap our things together, so we get silver carbonate, which is a solid, that's the important one, plus sodium nitrate. And we know that that's aqueous. Alright, so we've taken our types, aqueous, aqueous, solid, aqueous. Now we have to balance our charges. Well, silver's +1, nitrate's -1, so they cancel. Sodium is +1, carbonate is -2, so I crisscross them and I get Na2CO3. Silver carbonate, I have the same problem. This is +1 and -2, so I need 2 silvers. And sodium nitrate is +1, -1, so they're good. Alright, well let's balance. Well, silver, I've got 2 on the right and only 1 on the left, so I have to put a 2 there. That means I have 2 nitrates, so I have to put a 2 over on the right. And that means I have, let's see, 2 sodiums, and I have that, and 1 carbonate, and I have that, so I'm good. Okay, so I am now balanced. Alright, let's try another one. Alright, barium phosphate, ammonium chloride. See what you can do here. Alright, barium phosphate, I come across and I look at barium phosphate. Ooh, that's a problem. Remember, all of my reactants have to be aqueous. So barium phosphate is a solid. I can stop right there and say, this thing is a solid, so this reaction will not happen. So there's no reaction. That's simple. Done with that one. Alright, how about this? Iron 3 chloride and strontium hydroxide. Pause the video, see if you can do it. Alright, iron 3 chloride, strontium hydroxide. Iron 3 chloride, and sodium hydroxide. Sodium hydroxide is aqueous. So they're both aqueous, and when I figure out what I'm making, I should be making, sorry, that's wrong. I said strontium hydroxide, didn't I? Strontium hydroxide. Yeah, and strontium hydroxide is also a solid, so that's not going to work. So this has no reaction. And it has no reaction because strontium hydroxide is a solid, and remember, all of my reactants have to be aqueous. All right, folks, so you've got some to do on your own, so go ahead and see if you can do the worksheet. And again, ask Mrs. Sherman or myself if you have questions. We'll see you in class. Have a great day, folks. Bye-bye.